Hey everyone, welcome to our video on mass spectrometry. Mass spectrometry is part of the spectroscopy and spectrometry unit of OCHEM, and the best way to really prepare for this section is to do a lot of practice problems and also to understand the concepts behind how these processes work so that you can understand what the questions are asking you to identify and what they're really looking for in each of these processes. It's going to be a really brief summary of the high yield material. In terms of doing practice problems and being able to apply these rules, we're going to have a separate video for just practice problems on how to do this kind of stuff. So for spectrometry and spectroscopy, the point overall is to determine the information and the identity of an unknown substance. And this usually entails identifying things like what functional groups make it up, what the formula is, what the structure can be, and for the purposes of mass spectrometry specifically, we're trying to identify the molecular formula of the unknown substance. So for mass spec, we're determining the mass of ionized molecules using this external magnetic field. And so this is a typical diagram of what mass spectrometry looks like. So you have an unknown substance hanging out somewhere in here. You have this electron gun that shoots in and causes the substance to be ionized. And this can be represented by a formula that looks something like this. So it becomes ionized. These ions then shoot through into this magnet here, and here you have this magnet causing an external magnetic field that basically measures something called a mass to charge ratio. And the mass to charge ratio is represented by m over z, usually measured in atomic mass units. And the point of this whole process is to basically identify the right mass to charge ratio to represent what our actual peak substance is. So if you want to see like these three paths we have drawn here, let's say this one that I'm coloring in is our actual substance. This is the one that this pathway represents the mass to charge ratio of our actual substance. So the pathways to the left and to the right of it represent m over z's of heavier atoms or lighter atoms. And so it's really about varying the mass to charge ratio and varying the trajectory of this ion to make sure it actually falls to align with the proper substance that we're trying to identify. And the basis behind this whole process has to do with isotopes. So if you remember from Gen Chem, isotopes are elements with the same number of protons and electrons, but a different number of neutrons. So here I have, for example, hydrogen, and these are three isotopes of hydrogen. And of course, we have the atomic number, which is how many protons it has. We have the mass number, which is the number of protons and neutrons it has. And we have something called the natural abundance, which represents basically how much of the isotope you would be expected to find in nature. So if I were to do a worldwide hunt for hydrogen, I would find that 99.9% of the hydrogens that I find are protium or H1, this isotope version. Okay, so that's just kind of a summary of isotopes here. And sometimes you'll notice that the natural abundance is very, very little, to the point where it's negligible, because you hardly ever find something like this that exists, but it's there, just very negligible. So in mass spectrometry, we have an important chart that kind of represents what the detector shows up for you and what it measures. And this is what it looks like, the mass spectrum. And on the y-axis, we have the relative intensity or the relative ion abundance. On the y-axis, we have the mass to charge ratio or m over z. And some important terms that you should know include the molecular ion, which is represented by a capital M. And the molecular ion is the intact ion of the substance that we're trying to analyze. And if you imagine, it's basically, I'm going to go back to the previous two slides, it's basically that ion that goes into here that we're really trying to identify and measure. And the m over z value of this molecular ion is not always the highest m over z value, but it usually is. Like for our purposes, we can often assume it is, but just know that not 100% of the time is it always this value. And in terms of our classes, we don't necessarily need to look at a mass spectrum and point out exactly what each of these lines mean. It's more about being able to get certain pieces of information from the m over z value of the molecular ion. And you'll see what I mean by that as I kind of progress further in the video and also in the practice problems. Okay, and lastly for the molecular ion, just know that its m over z represents the molecule composed of the lowest mass isotopes. So if you have something like carbon-12 versus carbon-13, we're working with the isotopes of the lowest mass number. And some important other terms to know are m+1, which is basically the same thing as a molecular ion, but it's a heavier version of it. The mass is 1 more than m. m+2 is when the mass is 2 more than m. Okay, so for example, if we find that our m over z value, in this case, let's take a look at this mass spectrum. Our m over z value of m is 30. So here's our m over z of m. Sorry, that's going to be a lowercase m here. M over z of m is going to be 30. So our m+1 m over z is going to be 31, and our m+2 m over z is going to be 32. So it's basic addition here. And the last thing you also need to know for this is the base peak. And this represents the most abundant ion, or the tallest peak. So if we look over at our mass spec here, this represents the base peak. This is where it reaches 100% abundance. Let's take a look again at the mass spectrum, and basically the goal is again to determine the molecular formula of our unknown substance. So there's a series of rules that you should know that can help you narrow down what atoms and elements and how many atoms and elements make up our unknown substance. So how many carbons, how many nitrogens, etc. These rules will kind of help you figure it out and narrow it down. So the nitrogen rule is the first one I'm going to go over, and this is where you should start. You're looking at the m here, the m over z of m specifically. And if you notice that your m's m over z is even, that means you have an even number of nitrogens. And if you have an odd m over z value, that means you have an odd number of nitrogens. So again, remember from this mass spectrum here, m over z of our m is equal to 30. So this means that since this is an even number, we have an even number of nitrogens in our unknown substance. And just keep in mind this even number here means that you could have anywhere between 2, 4, 6, 8 nitrogens to 240 nitrogens to also 0 nitrogen. So remember 0 is an even number, so don't forget that value as well. The next rule that you should know has to do with how many carbons exist in our unknown substance. So if we know that our m+1 relative abundance given is 2.42%, the formula for it is you take the relative abundance of the m+1 and you divide it by 1.1%, and this gives you the number of carbons. And this 1.1% here is derived from the carbon-13 isotope. I'm not going to go into detail about exactly why this formula is derived this way, but just know that this is the formula and it comes from the carbon isotopes. So if we were to take this and solve how many carbons we would expect in our mass spectrum here, we would take 2.42% divided by 1.1, and this gives us 2.2. So this gives us basically an estimate of how many carbons we have. And I know 2.2 kind of rounds down to 2, but for our purposes, we want to be really, really sure. And so we're going to say that the number of carbons is anywhere between 2 to 3 carbons. So we know we have C2 or C3. And something to keep in mind is you definitely want to make sure you divide by 1.1 and not 1.0 because that can give you a different value. The next rule you should know is the H rule. So you have, and the H rule basically represents hydrogens and halogens and tells you the max number that you would expect for them. And so the rule for the H rule, the formula, is 2C plus N plus 2. So this tells you, you plug in the number of carbons that you think you have, you plug in the number of nitrogens that you think you have, and you add 2, and this should tell you the max number of hydrogens and nitrogens, or hydrogens and halogens that you should have. So just definitely memorize this formula. The next rule has to do with the M plus 2 molecular ion, and so the percentages are really important here in terms of the abundances that you will find in this peak. So if you find that your M plus 2 relative abundance is 4%, this represents the presence of sulfur. If you see that the M plus 2 abundance is 33%, this gives you an indication that it likely contains chlorine. And lastly, if it has 100% value of abundance, then that means that it likely indicates that it has a presence of bromine. So this is also something you should kind of memorize and take a look at, and be able to recognize these percentages if you see them as kind of a quick way to narrow it down. And then the last step is to determine how many oxygens you have. And this is really after you've determined, how many halogens, how many bromines and such that you have, and you take the masses and you subtract them to get this value here, the mass of how many nitrogens, oxygens, and hydrogens that you would expect. And there's also a specific table that you should set up, and I'm not going to show that here because it has to do more with solving the actual problem. But it can help you a lot to set up some kind of table to keep track of how many carbons, how many nitrogens that you've identified and such. And we'll do that in our practice problem video, which you can see us applying these rules basically. All right, so this is a summary slide of everything I just went over. So again, we have the nitrogen rule. You look at M, and specifically you look at the M over Z of M. And if it's even, it tells you that we have an even number of nitrogens, and if it's odd, it tells us that we have an odd number of nitrogens. So for our case today, we have M over Z is equal to 30 for our M here. So we have an even number of nitrogens. And this value here is actually super important in general because it can tell us how much our mass should add up to in total. So let's take a look at our carbons again. If you remember, we had determined that it's either C2 or C3. So we either have 2 carbons or 3 carbons. Now, if we know that our mass to charge ratio is 30, let's figure out how many nitrogens we're likely to have. So carbon has an atomic mass of 12. And if we were to basically calculate the atomic, the total atomic mass of this unknown substance, and let's say we assume that there are 2 carbons first. So let's say 12 times 2 is equal to 24. This is under 30, so that works. We could potentially have 2 carbons in our unknown substance. Let's also take the C3 assumption and see if that works. So we do 12 times 3 is equal to 36. So that's way more than the value that we have here. So that's actually impossible. We can't have 3 carbons here because that exceeds our molecular ion value here of 30. So we know that there's 2 carbons in our unknown substance. I'm going to write that over here. The next thing we need to look at is how many nitrogens. So we know that there's an even number of nitrogens, and we know that we have 2 carbons, and that puts us at 24 here. So that means that if we were to take a look at this, we have 30 minus 24, meaning that we have only 6 AMUs or atomic weights units left to work with. And we know that nitrogen's atomic weight is 14, if you remember from the periodic table. So 14 is, way more than 6 here. So it's actually impossible for us to have a nitrogen at this point. So we know that there's actually no nitrogens in our molecule, and the even number of nitrogens means that we have 0 nitrogens in our unknown substance. So if you remember from our H rules, 2C plus N plus 2. So let's go ahead and plug in our values here, and see what our max number of hydrogens and halogens could be. So again, we know we have 2 carbons, we have 0 nitrogens. How many hydrogens and halogens do we have? 2 times 2 is 4, plus 2 is equal to 6. So right off the bat, I can tell you that there's going to be 6 hydrogens here because the only amount that we have left to work with is 6 AMUs, and all the halogens have very large atomic weights compared to hydrogen, where we have 6 of them. So if you know that the atomic weight of hydrogen is 1, 1 times 6 is equal to 6. So we have 6 hydrogens in our mass spectrum here. So this actually is representing ethane represented below. This is the mass spectrum. And again, here's the intensities of sulfur, chlorine, and bromine that you can look at, as well as oxygen. And the last thing I wanted to go over in terms of information you should know is something called the double bond equivalent, or DBE. And this DBE tells us the answer to the question, does it have a pi bond or a ring? So the formula to calculate DBE is C minus H over 2 plus N over 2 plus 1. So this is basically, you take all the information you have found, you plug in the number of carbons you think there are, the number of hydrogens and nitrogens that you think there are, and this tells us how many DBEs we should expect. So if you get 1, then that means that you have 1 ring or 1 pi bond in your unknown substance. If you have 2 DBE, that means you have 2 rings, 2 pi bonds, or 1 each. And then you have 4 DBE, means you have it means you have a possible benzene. So these are just values that you should also become familiar with so you can recognize what each of these things indicate in your unknown substance. And keep in mind that your DBE cannot be a fraction and also cannot be negative. So if you get something like this, if you get a fraction or a negative DBE value, that means that you've calculated something wrong up here. Definitely go back and make sure you check your work and you can understand why you're getting this value. Okay, so that was a really brief, quick summary of mass spectrometry and the things that you need to know to solve the problems. Please refer to our practice problem video to learn more about what types of problems to expect and know how to do. So thanks for listening, guys.